Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 8, Multi-Area OSPF, Part 1. And there are two parts to this particular part of the course because there's a lot of detail here for you to master, not only to pass the BSCI exam, but also to work with OSPF in today's production networks. Because you've learned the theory of linked state protocols, you've certainly learned the theory of single area OSPF. But as those of you who have worked with OSPF can vouch for, there are very few network deployments in this world that use OSPF, that use single area OSPF. That's the theory that you need to know, but this is more real world. And believe me, there's a lot of theory here too, a lot of stuff for you to learn for your exam. And the first thing really is going to be a discussion about why we use multi-area OSPF in the first place, and why do we do that? When you first start studying for the CCNA, when you hit OSPF, and hit is probably the right word, you're hit over the head with area 0. You know, this is the backbone area. This is the important area. You got to have this. Every router you've got has got to have some kind of connection, physical or logical, area 0. And when I first started reading about OSPF, I would think, well, why don't we have just one big OSPF area 0? What do we need all these little areas for? As you're going to see, there are many practical reasons why you want to use multi-area OSPF. And I've seen plenty of large networks that were huge area 0s that could have realized huge production benefits in their routers, or performance benefits, I should say, by using multi-area OSPF. So what you'll learn here is great for the exam, but it's also going to be really good for your real-world skills. Then we're going to look at design guidelines, and as we all know, design guidelines in real world don't always go hand in hand. But these, I think, will help you out a great deal. They're also really good to know for the exam. These are Cisco's official design guidelines. They are guidelines, they are not hard and fast rules, but I have found that adhering to these really does help OSPF performance. Then we're going to move on to configuring stub and total stub areas. And I know that the theory of this is fairly simple to grasp, and the commands certainly are. It's one of these things where you type 2 words or 3 words and something's done. But it's something that we really need to see in action to really see the benefit of stub and total stub areas and to see how these things work. So what we're going to do is take the network from the previous video, from the single area OSPF video, and we're going to add 2 routers to it. We're going to add 2 new network segments. We're going to add another routing protocol. We're going to bring RIP version 2 into the picture, and you're going to see firsthand how beneficial stub and total stub areas can be to a router, and you will see firsthand the effects on the routing table, not just 1 or 2 screenshots. We're going to configure it, and you're going to see this in action. And that all brings us into an introduction to OSPF route redistribution, and actually to RIP route redistribution as well. Because if you're going to do something, we're going to do it right, and we're going to take some RIP routes and put them into OSPF, but also some OSPF routes and put them into RIP. And we do have a separate lesson in this course on route redistribution. It is such an important topic that you need to see it more than once, believe me. And the key here is to configure stub and total stub areas and have them work the way they would in a production network. We've got to perform some route redistribution. And we'll see why in just a few minutes. When we talk about multi-area OSPF to begin with, though, I mentioned, you know, when you first start reading your CCNA books, you get hit over the head with area 0. You also get hit with the word hierarchy a lot. Well, you know, OSPF allows you to set up hierarchies in this kind of design, and that's why it's so good. And that's fine, but what exactly does that mean as far as a network goes? When you introduce hierarchies into a network, you're classifying your levels according to various criteria into successive levels or layers. And that's the key. We get to build a layered network. With RIP and with IGRP, those are flat networks. All the routers pretty much do have the same role. They're all going to carry the same amount of the load. They're all sending out full updates. With OSPF, though, that's not the case. We can have our core routers, which most likely in our network are our most powerful routers. We can have them carry most of the load. And you're always going to have some routers on the outskirts of your network, perhaps the ones on your spoke networks closest to your end users. And while we would like everything to be the latest and the greatest, it doesn't always work that way. We don't always work for clients who can afford that kind of thing. If they have a 2500 router in production and it's doing the job for them, and you try to sell them a more expensive router, the first question is going to be, well, why should I do that? And if it's working, they don't want to spend the money on it. So we, as network engineers, have to be able to take a look at that and say, okay, they don't have the money. Maybe it's a school system. I work with a lot of school systems, and they can't spend, thousands of dollars on routers anytime they feel like it. So we could look at that kind of situation and say, okay, they're running OSPF, they're having some performance problems during peak times, but we can't throw money at the problem. What are we going to do? We will configure multi-area OSPF, because what that does, it allows you to lessen the load on your routers that can't handle that load, and meanwhile your core routers are the ones really calculating all the routes that have full routing tables. And the way that we save on router resources with stub and total stub areas as well, not just multi-area, but when we take it to the next level with stub and total stub areas, you'll see that we can really lighten the load on a router. So this isn't just theory. This isn't just something you're going to read in a book and forget about. This is stuff you can really use out there in production networks. I see it all the time. Because there are other benefits once we create those areas that aren't as obvious. One of them is the fact that we limit LSA traffic. We don't think about link state advertisements taking up a lot of bandwidth, and in a stable network they don't. But when you're using OSPF areas, and there's a problem in an area, there's a change in the network topology, only the routers in that area are going to be impacted by that. You're not going to have this change flooded throughout the entire network. So the notification of changes is limited, and in turn what that does is it limits the number of times that the SPF algorithm has to run. Because every time one of those little baby routers gets a change, gets an LSA update, it's got to run the SPF algorithm and recalculate the routing tables. That's something else we want to avoid our lower end routers having to do. And finally, and I know you'll enjoy this, this is what makes route summarization possible. And for those of us who have the basics of binary down, and I know you do, route summarization is another huge benefit. We can keep our routing tables smaller with route summarization. And we do have a look at OSPF specific route summarization in the next video. But just as a key here, you cannot summarize OSPF routes inside an area. You can't do it. You've either got to summarize them as they're being advertised from one area to another, or you summarize them as they're being injected into the OSPF domain by route redistribution. And you know that's got to happen at the ASBR. But that's multi-area OSPF makes that possible. Otherwise, we cannot summarize routes. Cisco's official design considerations for OSPF are on the board. And I know you can read, but I'll read them as well and add a couple things in for you. Again, these are considerations, these are guidelines, they're not hard and fast rules. I would know these for the BSCI exam, though. I would know these. And look at a couple of these, they're common sense. No router should be in no more than 3 areas, okay. No area should contain more than 50 routers. No router should have more than 60 neighbors. I have never seen a router have close to 60 neighbors, but they're out there. A router should not be a DR nor a BDR for more than one network segment. And then finally, don't run more than one OSPF process on an ABR if you can possibly help it. Once in a while, if you're running multiple OSPF processes, you're not going to be able to help that. But again, this all comes back to the fact that everything we configure on a Cisco router has a cost. And everything that a router has to do has a cost. It has a cost in router resources and against the CPU, against the memory. And the key here is that once you start violating these guidelines, once you start brushing up against these limits, you're going to start stretching the limits of your routers just a bit, or in some cases more than a bit. The one I see here that's violated most often, and it's one that's pretty easy to fix, is the fourth one, where a router shouldn't be a DR or BDR for more than one network segment. You want to watch that with Ethernet segments because, as I've mentioned before and probably will again before the end of this course, as far as the actual operation of OSPF is concerned, you don't really care which router on an Ethernet segment becomes the DR. You know, with the hub and spoke, we had to use the priority command to make sure that the hub became the DR. On the Ethernet segment, couldn't care less. But where we do care is maybe if that hub is also on an Ethernet segment, we want to make sure that it's not the DR or the BDR on the Ethernet segment as well, because being the DR or BDR for more than one segment does take up a lot of processor power. So those are just a few considerations for you, a few design considerations. Good stuff to know for the exam. And now we get into exam real world again, because the configuration of stub and total stub areas, it's really ignored in a lot of mid-sized networks. But I've used it more than once in those networks, and it has tremendously helped the performance of some of the lower-end routers. Again, we have to watch those. You know, not all routers are born equal. With a stub area and a total stub area, what they have in common is that they help to keep the routing table small, but they allow the router to properly do its job, to route packets. And we come back to that a lot here in the BSCI course. We want to keep that routing table as small as we can while still keeping complete IP connectivity. And how stub areas and total stub areas make this happen is that stub areas contain a default route, or the stub area routers will have a default route that represents the next hop IP address for all external destinations. And those are routes learned via redistribution. That's why we're going to do some route redistribution here shortly, so we can see how stub areas handle that. But when you hear about an external OSPF destination or network, it's referring to one that was learned by redistribution. Now what a total stub area does, it takes that concept one step farther, where the routers in the total stub area are only going to have one OSPF default route to reach external and inter-area destinations. So that can really lower the number of routes in the routing table while still keeping total IP connectivity for the router. We're now going to configure these, and we're going to see these in action. And first we'll have to do some route redistribution, which is great. It's a good introduction for you. And here is the network that we're going to use in this segment. And you see that at the core of this, routers 1, 2, and 3 are still running OSPF over Area 0. That's our frame cloud. Nothing different there from the previous video. The loopbacks are still there. They are still in areas 1, 2, and 3 respectively. Now routers 3 and 4 are connected via an Ethernet segment, and they have been placed or will be placed into area 34. And you'll notice we've taken the loopback from R4 off and out of area 4. That's because area 34 in this video is going to be used as a stub area and then as a total stub area. And one key rule for those is that a stub or total stub area cannot serve as a transit area for a virtual link. So if we still had router 4's loopback in area 4, we'd have to tear that virtual link down to make area 34 a stub. So we've just gotten rid of it. I know you know how to configure a virtual link, you know how to troubleshoot it, you know how to see the need for it, so we're moving on from there. Now we are adding a new concept at the top. We're adding a fifth router, router 5. Routers 1 and 5 are connected via an Ethernet segment, and we're going to use the network 15000 for that, /8. And you'll see that on the routers as we go through this. There are also 3 loopbacks, as you see on R5, those 3 lines coming out. And those are networks 6000, 7000, and 8000, respectively. We're going to see those, again, in the routing table as we go through here. So first thing we're going to do is take a look at router 1, which for some of you may be the first time you've seen a router running more than one routing protocol at a time. Always a recipe for danger. Let's see, we may still be, yep, hold on one second. And let's take a look at our pod, including, let's start with router 1 here, because this is, for some of you, maybe the first time you've seen a pod that, or a router that's actually running more than one protocol. And as you'll see, show IP OSPF is going to give you all the expected information, first about RIP and about OSPF 1. So, of course, you should be able to look at this and analyze what we've got running right now, but just as a quick review on some of this, with our RIP domain, I hard-coded it for version 2, so we have no version 1 updates or requests going out. I turned off auto-summarization with automatic network summarization not in effect. Here's the network that we're running it on right now, 15000. Our routing information source for RIP is 15115, which is router 5's Ethernet. And of course, there's our default administrative distance. And down here for OSPF, nothing we wouldn't expect to see. There's the RID. It is an ABR. Number of areas in this router so far is 2. There are the networks that we're routing. The frame relay is in area 0, the loopback in area 1. Here are the 3 routers we're getting information from, including ourselves. And the distance is 110. So, of course, as you'd expect here then, we have a couple of separate routing tables we can look at. Here is router 1's RIP routing table. And we see the 3 loopback networks, 5, 6, and 7. And just as we go along here, you always want to keep pinging and make sure that we've got connectivity as we expect to have it. We do. And as far as the neighbors go, show IP OSPF neighbor, we see 2 full adjacencies with router 2 and router 3. They're both DR others, as we would expect, because they're neither a DR or a BDR for this segment. But we also have, bring that back up, we also have an OSPF routing table. And we see router 2's loopback, we see router 3's loopback, and we also see the Ethernet segment connecting router 3 and 4. I've already put that into OSPF. So we see everything there that we expect to see. Now, going down, say, to router 3, will router 3 see those RIP routes? I haven't done anything special here. Let's look at its routing table for OSPF. And no, it does not, because router 1 is running both RIP and OSPF, but there is no default route redistribution going on here. You'll recall from your CCNA studies the times where that occurs automatically are very few and far between. One of the more bizarre ones is when you have IGRP and EIGRP running on the same router and they're using the same AS number. Remember that? They've redistributed automatically. You really don't want route redistribution to happen automatically. You really don't want that. I make a point of saying that about route summarization several times during the course. You really don't want route redistribution happening unless you're the one that's doing it. So going down to router 4 at this point, router 4, as you can see, let's bring the previous screen back up for just a moment. Router 4 is on the outskirts of our network, our OSPF domain. And there are a lot of destinations that router 4 might need to reach here. But the key is that it only needs 1 or 2 default route perhaps to reach any of these, because its next hop IP address is always going to be router 3's Ethernet. And let's take a look at the routing table on 4 just to verify that. And that's it. You see 4 different paths going to all 3 loopbacks and the frame, and R4 can connect with all of those, but what's the next hop IP address for every single one of them? 34.3. And every time this router's got to route a packet, it's got to look through this entire routing table, which right now is 4 routes. And you might think, well, that's just not that big a deal. But what if it was 20? What if it was 30? It might be a bigger deal then. Before we address that, we're going to do our first route redistribution, and we're going to go up to router 1 and take a look at that. And you recall the command show IP OSPF, and we can see that right now this router, as far as OSPF is concerned, is an area border router, an ABR. And we're going to see that change here shortly, because we're going to perform route redistribution on this router. And all route redistribution is the process of taking routes known by another method and placing them into another protocol. Now, those routes don't have to be learned via a dynamic routing protocol. We can redistribute static routes. We can, and are about to, redistribute connected routes. And routes that are being redistributed into another protocol, they're often referred to as being injected into that protocol. So when you hear about routes injected into OSPF, and I'll try to use that term here a couple times to get you used to it, it just means that routes are being taken from another source and put into the domain. So you're going to get introduced to a couple of basic, tricky OSPF commands here when it comes to redistribution. So we're going to go into router OSPF, and it should be OSPF 1, of course. See how the router stopped me from doing something wrong? You know, it said, hey, that's an incomplete command. The Cisco routers are almost always going to do that, but I'm going to show you one instance here in just a moment where they do not. And with router OSPF 1 on router 1, I want to redistribute the connected routes first, the connected interfaces, or networks, I should say. And I hit enter, and here's an instance where the router does tell me, hey, you know, maybe you don't want to use this command. Because if you use this, only classful networks get redistributed. If you want to redistribute subnets, and you almost always do, we've got to put the word subnets on the end of this command. We've got to do that. So what I'm going to do is take off the previous command and do a redistribute connected subnets. Now the reason that I put the connected subnets into OSPF is because the segment that's connecting router 1 and router 5, network 15.0.0.0, as far as router 1 is concerned, that is not a RIP route. That's a connected route. And this is one of the most common errors when it comes to route redistribution. Because it's not always enough just to take the routes from another protocol and put them into this OSPF domain. You've got to have the connected routes. Otherwise, if router 4 was trying to ping the loopbacks on router 5, it wouldn't know about that connected subnet, and the pings would not go through. It would look okay in your routing tables. That can be the hard part. Your routing tables are going to look okay, and you're going to say, why can't I ping these? And then you're going to realize that there's an intermediate network that's missing from the OSPF domain. So we've got to redistribute the connected subnets first. Now, we're going to redistribute RIP, and the same goes for the subnets. So redistribute RIP subnets. I left the S off there, but that's fine. It's the same effect. This is one-way route redistribution. We are taking the RIP routes and putting them into OSPF. There is no law that says we have to take the OSPF routes and put them into RIP. But we're going to do that in this case because we'd like R5 to have connectivity, total connectivity as well. And besides, we're going to send pings back and forth between 4 and 5, and those packets have got to know how to get back. So we are going to go into the RIP process from here. And we don't have to use the subnets command for RIP. Because I remind you, we are going to look at this in another video later, a little more in depth, and get a lot of practice with this. Because the commands are different and the requirements are different for every single protocol. So we're going to go through them as the course proceeds, and then we're going to have a big review section where you can compare all of them at one time. So let's take the connected subnets, because again, excuse me, just connected. Because again, why we have to do this into RIP is because the frame cloud here, router 1 doesn't see that as an OSPF route. It sees it as a directly connected route. So we've got to put the directly connected routes into RIP to have the connectivity that we want. So we're going to do that. Redistribute connected. And we didn't get any kind of message there, but I bet me saying we didn't get some kind of message is some kind of clue. And here we're going to put OSPF1 into the RIP process as well. Of course, that number is the process number. So everything, pardon me, looks fine. We go down to router 3 and do a quick show IP route OSPF, and all of a sudden we have a lot more routes here. And you see that the networks 5 and 6 and 7 are all coming in. And we've got 21030. We'll take that out because I left this in for a later lab. This is not a network that we're using right now, but I want to show you that you have to be careful with redistribute connected. But don't worry about that particular subnet right now. What we are looking at is routers 5, here, networks 5 and 6 I should say, and here are networks 7 and 15. They're marked with E2, and we're going to talk about that in just a moment, about what that E2 means. But let's go up to router 5 and take a look at the RIP table. And I don't see any of those other, I don't see any OSPF routes in here, do you? I don't see a 1. Let's go back to router 1 and make absolutely sure that we did it correctly. We'll do a quick WR here to save it. So for some reason here on router 5, we're not getting the OSPF routes that we thought we'd be getting. And there's probably a reason for that, especially since I'm saying it like this, right? There's probably a reason. But the router didn't tell us anything when we put these in. And here's the RIP configuration right here in the config, our RIP setup, and it's got redistribute connected and redistribute OSPF1. The problem here is that RIP requires what we call a seed metric. Redistribute OSPF1. And let's use OSPF help here. And notice, pardon me, that there's a metric here. Metric for redistributed routes. RIP requires that a seed metric, or what basically it's kind of a starter metric, be set for routes that are being redistributed into RIP. Because for RIP to look at the OSPF cost, it's going to be higher than 15, right? It's going to be much higher than 16, which is unreachable. So the OSPF metric really makes no sense to RIP. So you have to give it basically a starter metric or a seed metric. And I'm going to go ahead and do the same for the connected routes. We're going to clear our routing table, do a WR on the way out, see how that goes. Because again, this is something that RIP requires. Ah, look at that. All of a sudden, we've got all the routes we expected to see. We've got the loopbacks on 1, 2, and 3. We've got the Ethernet segment here at the bottom that's connecting routers 3 and 4. But you'll also notice way back when we did this to begin with, that we got no warning message from the router that there was even a problem. See, when we put that in, the router didn't tell us, hey, you got to put a seed metric on here. I'm not exactly sure why the router doesn't say that, because it is a requirement. And I've asked Cisco, and I've never really gotten a straight answer on it. So that's one of those things you just got to know, because otherwise it's going to drive you crazy, because you're going to keep looking at your RIP routers and saying, well, why isn't this working? Why isn't this redistribution working? So keep in mind, we'll mention this again later, but that seed metric is required for RIP, IGRP, and EIGRP. And you might think, well, why didn't we have to do that with OSPF? OSPF uses a default seed metric of 20. That is, OSPF uses a default seed metric of 20, he said again, and therefore we don't have to set a metric for the connected and the RIP subnets that we brought in. Now let's look at the effect that has on router 1's OSPF role in this network. We ran show IP OSPF again, and we can see now that R1 is both an ABR and an ASBR, an autonomous system border router, or as the router actually says, autonomous system boundary router. You hear people call it an autonomous system border router all the time. Any router performing redistribution in OSPF is a ASBR. So now you've actually seen your first route redistribution in action. Before we look at 4, another good way to see all the ABRs and ASBRs is with this interesting command, show IP OSPF border routers. And I put border route. The full command is border routers. And here we can see that in this process, the router at 2.2.2.2, which is router 2, we know that it's an ABR. And so is router 3. That's a good command to run if you're just walking into a giant OSPF deployment. Maybe you're doing some troubleshooting or some addition. And it's always good to get the lay of the land before you get started on something like that. And here, show IP OSPF border routers will do that for you. So let's go down to router 4 right now. And just as a reminder, we'll take another look at the drawing here. We have redistribution configured on router 1, and we're going to see what router 4's routing table looks like at this point. That's filling up pretty good there, huh? Getting pretty big. Now we've got quite a few IA routes and about 5 E2 routes. And we have connectivity to the loopbacks on router 5. We're going to ping all of them here just to make sure. We do, there's no problem. So we have connectivity, and again, this is not wrong, but it's a waste of resources. Because if you'll notice, and I'm not even going to highlight for you here, you'll notice that in every single one of these routes, both external and inter-area, the next hop IP address is the same. So there's no reason to have a full routing table like this, because this could be an end-of-life router, this could be a little baby 1700 routers, no telling what this router could be. But however hard it's having to work to make routing happen, it's working too hard because this table is too big. It does not need to be this large. So what we're going to do to begin with is make this area a stub area, area 34. Because that's going to knock out all the external routes from R4's routing table and replace them with a default route with the next hop of router 3. So the configuration for this is very simple. It's a lot like the variance command with EIGRP. Configuring it is easy. Figuring out when to configure it is not that easy. But here we've got a really good candidate for a stub area in area 34. So let's configure that. The command is very simple. One thing you need to really remember about it, though, we're going to see it in action in just a second. Area 34 stub, that's it. And I just configured this on the ABR. And man, my adjacency went down almost immediately. Now we've seen that happen before and the adjacencies come back up. Let's see what happens this time. Let's see if that adjacency comes back. This is an Ethernet segment, so if it was going to come back, it'd come back pretty fast. Doesn't look good. Doesn't look good at all. Let's go over to router 4. The problem here is, and I don't think we're going to see anything different here. Nope, nothing. The problem here is that we have set the stub flag, or set the stub bit, depending on how you want to put it, in the hello coming from router 3. But router 4 is not yet set as a stub router. That's one of the things that routers have to agree on to keep an adjacency, is whether or not the area they're connecting through is stub or not. So let's go on router 4. OSPF 1, area 34 stub. And we'll see how it goes. We'll save our work here. And I have a feeling we're going to see that adjacency come back up pretty fast. We're building our config, and by the time that finishes, we'll probably have our adjacency back already. And we do. It's already up. Router 3 is the BDR. Everything's fine. Let's take a look at that routing table. Wow. We already cut it in half. The E2 routes, which are the external routes, are gone. And they have been replaced by a single default route using 172.34.34.3 as the next hop. And as you recall, that asterisk indicates a candidate default route. So this may be the first time you've seen it. I'll bring the full table up. And I know you remember that that asterisk marks candidate default, but many of you may have just seen static default routes up to this point. So there's your first OSPF static route. Well, we knocked the heck out of that table, because let's take a look at the full OSPF table a moment ago. What did it have, 11 routes? That's a lot of routes for a little baby router maybe. And just that quickly, with one simple command, we knocked that table size down in half. And we can still ping those external destinations. So we have not lost any network connectivity, but the router now has to literally work half as hard to perform its routing. Now you'll notice here, let's run show IP route OSPF one more time. You'll notice here, of course, the AD is 110, and the cost right now is 11. And if you need to change the metric for this for any reason, and in the real world production networks, I've done it very rarely, but it's a good skill to have, we can go to the ABR and change the default cost of that route. Let's see what the range there is. 0 to, yeah, I wouldn't set it to that maximum. Let's not do that. Let's set the default cost to 20 for the default route. And again, that command is area 34 here, area X, default cost. And what we're doing is changing the default cost of the default route. And here it's 30, and if you're familiar with your OSPF cost, you know why that went up by 10 before it got here. But the default cost is now 20. Just cute little command to know. So now we're going to take this one step further, my friends. We're looking at this table, and we're out there on the job, and we're saying, okay, you know, we've done a good job here. We've done half the job, but now we're going to do the other half. Because the next hop for every single inter-area route in this table is 34.3. So we're now going to make this a total stub area where all external and inter-area routes will be replaced with a single default route. We're going to go to the ABR of area 34 again, which is router 3. And there's router OSPF 1. Here is the command. You simply repeat the area 34 stub command with no summary at the end. And something different happened this time, or didn't happen. The adjacency did not drop after I configured this. Maybe that's a little suspicious. Let's take a look. Still have our adjacency. Let's monitor that dead time. The dead time just went up You could see in the first one it was 30 seconds for the bottom for the adjacency to 4, and it went to 35 right after that. So it's being renewed by hellos. The hellos are going through properly. Still there. Let's go down to router 4. Don't think we'll see anything unusual here. Nope. Let's look at the routing table. Wow. We're down to 1 route. It already took effect. There is no such thing as a total stub flag bit in the hello. The only thing that routers 3 and 4 have to agree on right now is that area 34 is stub. And total stub is just an advanced or accelerated form of a stub area. So once you configure the area as stub, you'll see the adjacencies go down until all the routers in the area agree that it's stub. But then adding the no summary command to the ABR is not going to bring the adjacency down. Now you'll notice that we did not have to bring or configure the no summary option on router 4. It would not hurt anything if we did, and I see occasionally configurations where no summaries on every router. It doesn't hurt anything, but it doesn't do anything either. It's good detail to keep in mind for the exam. The only time you've got to put no summary on is onto the ABR itself. But now look at this. We had all these routes, 11 routes or so, in router 4's routing table. We configured it as a stub area, area 34 that is, and that quickly knocked it down in half, as we see here. And we still had IP connectivity. And then finally, by configuring it as a total stub, we take it one step further, and now we're down to a single OSPF route. This router can still ping any frame relay interface. It can ping the remote loopbacks. It can ping anything in this network, but now instead of having to do a lookup through 11 routes, it just has to look at 1. And that is a bonus no matter how you look at it. That is fantastic. So, you know, we always want to take stuff a step further. Now, it's hard to take this a step further. We're down to 1 route. We got to have 1 route. we can't knock it down to no routes here with OSPF. But if it's such a great idea to make an area stub or total stub, how about making area 0 a stub area? Can we do that? It might not be a good idea here, but would it ever be a good idea to make area 0 a stub router or stub area? Let's go to router 1 and find out. What do you know about that? The router is not going to let you do that. You will immediately get a message saying that your backbone area cannot be configured as stub. And like I said, one of the things I like so much about Cisco is that 9 out of 10 times, probably 99 out of 100, when you're about to do something you shouldn't do, the router's going to tell you, or at least warn you. In this case, it doesn't even let you do it, because you've got to have full LSAs flowing through area 0. And as you'll see in the next video, when we have stub areas configured, we will have certain LSA types that are allowed and certain ones that are not. But by area 0 being the backbone of your entire area, you can't limit the LSA flow. You got to have a full flow.